Hi, AP Stats. Today we're going to begin Chapter 10, and Chapter 10 is about comparing two populations or groups. So we're going to intro Chapter 10 with 10.1, and if we take a look here, our learning target is going to be to describe the shape, center, and variability of the sampling distribution for a difference of proportions. Now this is going to be very similar to what we did back in Chapter 7, we had to describe the shape, center, and variability of a sampling distribution of one statistic, a proportion, or a mean. Okay, so there's a YouTube video, which I haven't put on here, but I can put on Schoology, that actually talks about this experiment that was done on the Mythbusters. And the question they were looking at was, is yawning contagious? So let's take a look. It says, Mythbusters investigated this question. Here's a brief recap. Each subject was placed in a booth for an extended period of time and monitored by a hidden camera. 34 subjects were given a yawn seed by one of the experimenters. That is, the experimenter yawned in the subject's presence before leaving the room. The remaining 16 subjects were given no yawn seed. Draw an outline of the Mythbusters experiment. This takes us back to the beginning of the year when we were talking about experiments in Chapter 4. So let's draw the outline. We have 50 subjects, and then in an experiment, you're going to randomly assign your subjects. So the first thing we're going to do is our random assignment. And we're going to randomly assign them into two groups. The first group had 34, and the second group had 16. Then they went ahead and they applied the treatments. The treatment that they applied to the group of 34 was the yawn seed. And then group 2 is really the control group. They didn't have a yawn seed, so this one had no seed. And then at the end, what they went ahead and did is they compared the yawning. Okay, so let's take a look at the Mythbusters results. Here are the Mythbusters results. You can see it's broken up to whether or not the subject yawned, and then if they got the yawn seed or not. So we're going to call P1, our parameter, the true proportion of people who, given the yawn seed, will yawn. So this is conditional probability. We're going to take it out of the total of who were given the yawn seed. So we're going to say who was given the yawn seed and actually yawned. If we take a look at that, there were 10 subjects that actually yawned given the yawn seed, and we had out of 34. So this is going to be 10 out of 34. Our statistic P1 hat is 10 out of 34 for that group. And if you divide that out, it's approximately 29%, so 0.29. Now for our second group, we're going to call P2 the true proportion of people who, given no yawn seed, will yawn. So we're taking it out of those that were given no yawn seed. So here's the no yawn seed. So those that had no yawn seed and yawned were 4 out of 16. So 4 out of 16, we know that reduces down to 25%. So 29% yawned when given the yawn seed, 25% yawned when not having a yawn seed. So it says, what is the difference in the proportions? So I'm going to go ahead and calculate the difference. Well, 29% minus 25% breaks down to 4%. So there's a 4% difference between the two groups. So the question says, does the data provide some evidence that yawning is contagious? What do you think? Well, if we take a look, the group that was given the yawn seed had a higher percentage of yawns than those who were not given the yawn seed. So we do have some evidence. So we're going to say yes. People given the yawn seed yawned more often than people not given the yawn seed. Okay, so there is some evidence just with this one experiment that they conducted on the 50 subjects. But now it says that Adam Savage and Jamie Heineman, the co-hosts of Mythbusters, use these data right here to conclude that yawning is contagious. Do you agree? Because they found that in their experiment right here that 4% more in the yawn seed group yawned compared to those that were in that didn't receive the seed. Could it just have happened by chance? So we really don't have convincing evidence right now just to automatically say, oh, because we did this experiment one time with this group of 50 subjects that because our difference is 4% with those who yawned with the seed compared to those that didn't. So no, it could have happened that people who got the yawn seed yawned more often purely by chance. It's not necessarily convincing evidence for us. So we're going to state no. It could have happened that people who got the yawn seed yawned more often purely by chance. Okay, so let's go on to the next page. All right, so we're going to take a look at this, and it says in this activity, which we would have done if we were in class, we're going to investigate whether the results of the experiment are statistically significant or if they could have occurred purely by chance. Okay, let's go back and restate that question. All right, in this activity, your class will investigate whether the results are statistically significant, which means that they don't happen by chance, or that they could have occurred purely by chance due to random assignment. So again, we want to talk about here that this is an experiment, so we're not having random sampling, we are having random assignment. So what would be the null hypothesis? Now again, I'm going to introduce this to you today, but we will develop this more in the next couple of days. So the null is, we're going to want to see, they're convinced that yawning is contagious, right? So again, the alternative is what we want to test, what we want to prove true, we want to test it against the null. So if they're trying to prove that yawning is contagious, our null would be that yawning is not contagious. So if yawning is not contagious, that means when I would take the proportion of those who yawned with the yawn seed and compared it with those who yawned without the yawn seed, in order for it to not be contagious, they would have to have the same proportions. So if we were to subtract them, it should be equal to 0. Okay, so we understand that to mean that yawning is not contagious. Now again, the alternative is what we want to test against the null, and they made the statement wanting to say that yawning is contagious. If yawning is contagious, when we would subtract these two, we should get a positive number, so we would actually make this become greater than 0. So if we go through and test this and we find that and our number is greater than 0 and it's not statistically significant, then we can go ahead All right, the 50 people in the experiment are represented by the cards. A person is either a yawner or a non-yawner, no matter which treatment they are randomly assigned. Shuffle the 50 cards and put them into 2 piles. One group of 34 that gets the yawn seed and one group of 16 that does not get the yawn seed. Record the proportion of people who yawned in each group. You will do this 3 times. So if you had been in groups in class, you guys would have done this 3 times and gotten your results. So here we go. You can take a look. This is just a picture of conducting that experiment. Here is our group of 34, and if you count out of those 34 that received the yawn seed, you would have counted that there were 11 out of the 34 that yawned. Then if we go over here, this is the group that did not receive the yawn seed, the 16. If we were to count them, we would see that 3 out of the 16. And you would have conducted 3 trials of this, okay? And then you would have gone through and you would have listed your trials. So our first one was 11 out of 34, which is approximately 0.32. And then the second one was 3 out of 16, and it was approximately 0.19. And then we would go ahead and find the difference in proportions. And when we would do that, it's about 13%. That was the difference in the proportions. So we would have went through, your group would have did that 3 times, and then we would have collected data. But since we're not in class, we're going to use data from another class who did this activity. And you can see right here all the data that is collected. Now, we're taking a look at what we're taking a look at is the 4%, right? We saw that they are saying 4%. Because they got the 4%, they made the conclusion that yawning is contagious. Again, we're going to take a look at the direction of our null, the direction of our alternative. We know that it was greater, our alternative was greater than 0, so we're going to think about how often does 4% or higher occur, because we see that that's greater than 0. Now, if you look at your chart, you're actually going to see that in this whole chart, 4% only occurred 1 time. All right, so let's take a look. You guys would have went through and you would have made dot plots with all the data in our class. So I went ahead and took that data and made a dot plot for you. And normally we call this a sampling distribution. And this actually, because it's an experiment, is not a sampling distribution. We would call this, and I'll write it up here, it is a randomization distribution because it was an experiment, not just a sampling distribution. So it's a randomization distribution of the difference in proportions. In this case, it was p hat 1 minus p hat 2. Okay, so what does each dot represent? Each dot represents a sample of 50 subjects broken up into the 2 groups and calculating the proportions and taking the difference of each proportion, and these are each of the differences. Okay, so the question says, in what percent of the class trials did the difference in proportion equal or exceed 4%? Again, it's always in the direction of the alternative hypothesis. Basically, what they're asking you to find is the p-value. Now, on the AP test this year, because you are not going to be using you don't necessarily have to use a statistical calculator. This is how they will most likely, if you have to find a p-value, it's not going to be from a table. It's going to be from a data display. Okay, so it'll be something like this here. So we're going to take a look, 4% or higher. If we go ahead and look, this value right here is probably that 0.404 that we saw. So 4% or higher would be these points. So to find the p-value, you're going to take the number of circled dots and you're going to divide that by the total number of dots. So again, on the AP exam, if you have to do this, it's going to be from some type of simulation like this. That's most likely how you would have to calculate a p-value. Otherwise, they may just give you the p-value. All right, so in this case, our p-value is equal to, if you count those dots, there are 13 out of them, 13 out of 25, which is approximately 0.52. Remember, our p-value is the probability that the sample data occurs given your null hypothesis is true. So given that yawning is not contagious, our sample data, our difference in proportions to get 4% or higher is going to occur about 52% of the time. So it says, what conclusion can you draw about whether yawning is contagious? Well, our p-value of 0.52 is greater than our significance level of 0.05. Remember, if they don't give you a significance level, you're going to use 5%. And when it is greater, we are going to fail to reject the null hypothesis. And if you go back and take a look at our null hypothesis, the differences in the two proportions, P1 minus P2 equals 0, that was meaning yawning is not contagious. So we're going to fail to reject that. So here's what that tells us then. Therefore, we do not have convincing evidence against our null. But we don't want to just say against the null. We want to give it in context. So we do not have convincing evidence that yawning is contagious. So we just busted the myth busters. They made the conclusion that yawning was contagious based on their numbers, but they didn't put it to any kind of test. Okay. All right, so like I said, we are going to go through and we are going to be dealing more with these problems in the next couple days. So we went through it quickly. If this is something you struggle with, just keep reading your textbook and keep going along with the lessons as we continue this the next few days. Okay, so we did that problem, but the main idea for this lesson is we want to talk about the shape, the center, and the spread of a sampling distribution of difference of proportions. And this is very similar to what we did back in chapter 7. It's the same idea when we were trying to talk about the shape, center, and spread of a sampling distribution of a single statistic. So our shape that we're going to be looking for, our shape we're going to look for hopefully is approximately normal. And to test if it's approximately normal, we're going to use our large counts. But now we have two proportions, so we have to do it for both proportions. You'll take the sample size times P1, and then you'll take the sample size from the first set times 1 minus P1. Remember, it's a successes and failures, and they both should be greater than or equal to 10. And then you're going to go ahead and do it for your second set. N2 times P2, N2 times 1 minus P2. Both of those should be greater than or equal to 10. The center. Just like we had a sampling distribution, when we would have the mean of p hat, it would be equal to the parameter. It's going to be true for our mean with our difference of proportions. If we're going to take the mean of the difference of the proportions p hat 1 minus p hat 2, it's going to be equal to the parameter p1 minus the parameter p2. Now we're going to talk about spread. Usually when we talk about spread, we talk about standard deviation, which we are going to talk about standard deviation. But we can only use the standard deviation if our groups are independent of each other. So when we're taking a look at our random samples, or in this case, it was our randomized assignments, each group should be independent of each other. There should be no overlap. Otherwise, we cannot talk about the spread or the variability. So before I give you that formula, I'm going to go the long way around because I don't like just to give you formulas without explaining the math. So we're going to take just a minute to go through this. So here's the sampling distribution of p hat 1. The statistic would just be p hat 1 because that's your statistic. The parameter would just be p1. The mean of the statistic, we know, we already talked about that, would be equal to the parameter, so it would be P1. And then standard deviation of the statistic, if you remember from previous units, the standard deviation in this case will be P1 times 1 minus P1 all over n. We've used that formula many times. Now we're going to go through and take a look at it for the sampling distribution of p hat 2. So the statistic is p hat 2. That's how we know it's the statistic, because the p hat, the parameter would be p2. The mean of p hat 2 will just be the parameter p2. And then our standard deviation of p hat 2 is going to be equal to the parameter p2 times 1 minus p2 over n2. And I should go back up here and state this should be n1. Okay. All right, so now sampling distribution. Let's talk about when we're going to put these together. So statistics sampling distribution is just going to be p hat 1 minus p hat 2. So the parameter, we're allowed to just subtract the parameters p1 minus p2. The mean of p hat 1 minus p hat 2 will be equal to the parameter p1 minus p2. Now, standard deviation is where we have to be careful. We learned in chapter 6 that when random variables, when combining, you cannot just add standard deviations. Okay, the way to get around that is to find the variance first, and then we can go ahead and take the square root. So when combining random variables, you can't add standard deviations. You have to add together their variances. So that's where I wanted to show you where that formula came from. So variance is our standard deviation squared. So if I have this variance of p hat 1 minus p hat 2, then I would take the variance of p1, and I would add to that the variance of p2. Now we'll go through and calculate that out. So let's see. Actually, I think it should be this. You should have the hats on. I need to double check that, but I think so. Okay, so we'll continue to show the work for that. So we're going to use our formula for standard deviation, which is right over here, but to find the variance of that, we're going to square it. So it's going to be the square root of, and it's actually p1. So it'll be p1 times 1 minus p1 over n1, and we're going to square it. Then we're going to do the next one. It's going to be p2 times 1 minus p2 all over n2, and because it's variance, we square it. Now what happens is the squares and the square roots cancel out, so our variance is really equal to p times 1 minus p1 all over n plus, should be n1, p2, fix that, I'm sorry, plus p2 times 1 minus p2 all over n2. Okay, so now we're going to go through, and to solve this, we would just go through and take the square root to get the standard deviation. P hat 1 minus p hat 2, it will be equal to the square root of this entire thing. Okay, so that would be our formula. So again, I just wanted to take a couple minutes to show you where that formula is derived from. I could have just said, here's your formula and here's how you use it, but I want you to understand that when we are subtracting proportions, we just cannot subtract the standard deviations. Also, some students say, well, why do we add even though we're subtracting? It's because it's variability. Whether you're adding or subtracting variables, you have more than one, so there's going to be more variability, so we will always add when we're finding variances. Okay, so let's go back to the top. We'll fill that in. The formula that you are going to need is going to be standard deviation of p hat 1 minus p hat 2 is equal to P1 times 1 minus P1 all over N plus P2 times 1 minus P2 all over N. And again, this should be N1 and N2 because they're from different sets. Okay, now again, I said you can only use this when the random samples or the random assignments are independent of each other. Okay, so let's go ahead and let's take a look at the practice problem. We are going to be using shape, center, and spread. I'm not giving homework on this, but it's just to introduce where we're going with the chapter, and you may have to answer questions about that later on. Okay, so let's do the check our understanding. It says, your teacher brings 2 bags of colored goldfish crackers to class. Bag 1 is 25% red crackers. Bag 2 has 35% red crackers. Each bag contains more than 1,000 crackers. Using a paper cup, your teacher takes a simple random sample of 50 crackers from bag 1 and a separate simple random sample of 40 crackers from bag 2. Let p hat 1 minus p hat 2 be the difference in the sample proportion of red crackers. So we'll go ahead and just have p hat 1 represent the sample proportion from bag 1 and p hat 2 represent the sample proportion from bag 2. So what is the shape of the sampling distribution of p hat 1 minus p hat 2 and y? So we're going to check for the normality. So for bag 1, it told us that we had a simple random sample of 50 crackers with P1 should be equal to 35%. I'm sorry, 25%. So we're going to set that up and we're going to check our large counts. So from bag 1, it was 50, and then our P1 was going to be 25%. So 50 times 0.25, and then we're going to do 50 times 1 minus 0.25, which is 0.75. And we're going to go ahead and calculate this out. This is going to be 12.5, and this one is going to be equal to 37.5. That's greater than or equal to 10, so that checks. So let's go ahead and take a look for bag number 2, where we had a sample size of 40 crackers, and our P2 value was equal to 0.35. So again, we'll set that up, 40 times 0.35, and then we're going to have 40 times 0.65, and we simplify each of those out. We see that they're both greater than or equal to 10, so therefore the large counts checks, and we're going to say it is approximately normal. All right, find the mean of the sampling distribution. So we know that the mean of the difference of the sampling distribution of proportions is going to be equal to P1 minus P2. And in this case, that's 0.25 minus 0.35, and that's equal to negative 0.10. Now for the last question, calculate and interpret the standard deviation of the sampling distribution. So for our standard deviation, and again, this formula is these are on your AP exam formula sheet, so you don't have to have memorized. And again, you should hopefully have that printed off so you can see it. P1 times 1 minus P1 all over N1 plus P2 times 1 minus P2 all over N2. So if we plug our values in for that, it's going to be 0.25 times 0.75 all over the first sample had 50. Or the first bag had 50, I should say. And then 0.35 times 0.65 all over 40. And you can pause it and put it in your calculator, but it's going to come out to about 0.097. So now I asked you to interpret standard deviation, and standard deviation tells you the average variation from the mean. So we are going to state that the difference in sample proportion, I should say sample proportions, typically varies by 0.097 from the true difference in proportion of negative 0.10. Of negative 0.10. Okay, so there you have it. That is how we take a look at shape, center, and spread of sampling distributions of difference in proportions. Again, if you struggled with that first problem about how to set all that up with the null hypothesis, that's where we are going, and we will continue to work on that in days ahead. So thank you for listening. Thank you for taking a look at that proof with me. I hope you guys have a good night. I'm not giving homework to follow up with this, but please have this completed so you will be ready for our next lesson. Have a great night.